Let's talk about naming metamorphic rocks. And this is something that students find pretty tricky because there are a lot of prefixes that you might add on to be more specific about the composition of the rocks. I'll give you an introduction to foliated and non-foliated metamorphic rocks, give you some specific metamorphic rock names to use, discuss protoliths and the metamorphic minerals and rocks that are associated with them, and then I'm going to give you a tool to use that'll help you, it's a flow chart to name metamorphic rocks. So when you name a metamorphic rock, you have to say something about its composition and its texture, whether it's foliated or not foliated. You have to address both of those in a metamorphic rock name unless it has a specific name to use. So foliated metamorphic rocks basically have four terms to use. We can use the term slate to describe a very fine-grained metamorphic rock that has a well-developed cleavage. And if you think of a chalkboard slate, it's very flat, is narrowly defined layers that are the cleavage. And a phyllite. This is a phyllite here. The difference is, in the phyllite, it forms at slightly higher grade than a slate. And so this sheen that you see results from aligned small grains of phyllosilicates, maybe a chlorite, and certainly very commonly muscovite. And so if it has a sheen, it is at a higher grade than slate, and you call that kind of rock a phyllite. You might also have a schist, and this is a nice example of a garnet schist. These are large garnet porphyroblasts there. And a schist is a rock in which the micas, and you can see the sheen of the micas there, the micas are laying flat within the foliation plane, within that cleavage plane, and the micas really define the layering, define that foliation in a schist. And that's higher grade than a phyllite, and you start to see the development of porphyroblasts, or these large crystals that are growing within higher grade rocks. The other foliated rock type is a gneiss, and that's, you can see the spelling here, G-N-E-I-S-S. And a gneiss is slightly higher grade than a schist, and in a gneiss you're seeing a layering, so a compositional layering that's in this rock defined by these lighter colored minerals there versus darker colored minerals there. And when you see this banding or this layering that's no longer defined by an alignment of the muscovites, that is when you call a rock a gneiss. So those are textural terms and don't really tell you anything about the composition of the rock. But looking at this gneiss, it appears to have a few dark minerals, a lot of light colored minerals. In its former life, it probably was a granite. Now let's take an example of a granite in this diagram, where the crystals are all oriented kind of randomly. There's no structure to it. If we deform the rock during regional metamorphism, and when we're thickening the crust and folding and faulting the crust, there are going to be stresses that we denote with sigma 1, sigma 2, and sigma 3. And sigma 1 is the greatest compressional stress. Sigma 3 is the least compressional stress. You can think of it as a stretching direction. And in this diagram here, we have a greatest compressional stress that is vertical. And what happens is, if you've got a granite, there are elongate minerals like hornblende or platy minerals like muscovite and biotite that end up aligning perpendicular to that greatest compressional stress. And that texture of alignment, whether it's a schistosity or whether it's a gneiss texture, that's defining a foliation, or it's a planar structure that defines that layering. Now, we aren't necessarily going to get vertical greatest compressive stresses. And of the 3 compressive stresses, they all may have different magnitudes. So if in a situation where we have sigma 1 that is larger than both sigma 2 and sigma 3, but sigma 2 and sigma 3 are similar, we're going to get a foliation, but there will be no lineation. There won't be an alignment in the length of those elongate minerals. And if we have the greatest compressional stress equal to the intermediate stress, and those are both greater than the least compressional stress, that extension direction, you're going to see a lineation forming. And if you see a foliation in this rock that is a planar structure, and the rock above it, you see that instead of flat minerals aligning in the foliation, on the end of this rock you see points. And those are points of those elongate minerals that are lined up in a lineation that define the direction of that least compressional stress. So you can determine the orientation of that sigma 3 direction if a rock is lineated. Now, if the greatest compressional stress is larger than an intermediate compressional stress, and that's larger than the least compressional stress, you'll see both a foliation and a lineation. So whereas it might not look as well lineated as this rock, in the foliation plane, you may be able to see individual small minerals that are aligned in a particular direction that define sigma 3. So when we're looking at rocks with a foliation and or a lineation, we're seeing deformation that's resulting from a ductile deformation. And if there is differential stress applied to that rock where sigma 1 is at an angle to the vertical orientation, you're going to end up getting shearing. And that's denoted by these arrows here that show that the top is being sheared to the right, the bottom is being sheared to the left, and where you've started with a circular mineral, you end up deforming it and shearing it in a particular direction. So that tells us something about the kind of deformation, and this is also called non-coaxial. And I'll explain this in the next slide. So as in the last example, we start off with a round mineral and apply some stress at an angle. So sigma 1, your greatest compressional stress, is oriented like this. You're going to end up deforming the rock and shearing it non-coaxially. That means those stresses are not, there are no 2 equal stresses in the rock, that they're all differing in some way. And a good example of that would be the stretched pebble conglomerate here. And these blobs that look elongate are stretched pebbles. And we assume they start off as rounded pebbles in some conglomerate on some riverbank, were buried and lithified. And then at some point during deformation and metamorphism, the rock was deformed non-coaxially. We can see the direction of least compressive stress because it lines up with the stretched pebble that form a lineation in the rock. And those fall within the foliation plane that's parallel to it. And we can say something, it's not precise, but we can say something about the greatest compressional stress because it must be at some relatively high angle to sigma 3. because it's formed this foliation and it's caused this non-coaxial deformation. Now, we can also have a coaxial deformation, and that's where we start off with the same rounded pebble or rounded mineral, and we apply some sigma 1 stress that is matched by an equal sigma 3, and sigma 2 would be coming out of the plane of the page. And what that results in is a flattening, or, as I like to point out, a pancaking of a rock. So instead of a stretched pebble forming a lineation, we're actually forming little pancakes out of those pebbles. Now we have non-foliated metamorphic rocks too, and those have more generic names. Now we just talked about slates and phyllites, schists, and gneisses being the foliated rock names. For non-foliated metamorphic rocks, we basically have two choices. It's either a hornfels, that is a very fine-grained rock that forms in contact aureoles, or we have a granophyls, which is a coarse-grained rock with no particular texture. And I'll get to how you use these names to actually name a rock. But if there is no foliation, then you can't apply slate, phyllite, schist, or gneiss, and you must choose one of these terms. There are some specific metamorphic rock types, though, that if you see a rock that falls into one of these categories, then you have a specific term that you should use to name the rock. For instance, if you metamorphose a limestone or a dolomite, it's dominantly carbonate mineral, you're going to end up with a marble. And it's simply, in my example from a previous lecture, it's resulting from a coarsening of and a recrystallization and coarsening of the carbonate grains. If you're starting off with a relatively pure sandstone that's comprised mostly of quartz, you metamorphose that, and that's going to recrystallize and form what's called a quartzite. If you're metamorphosing an ultramafic rock that is rich in magnesium and iron, you are going to form a serpentinite. And it has a texture, a luster to it from the serpentine, from the phyllosilicate serpentine, and a color that helps you to identify serpentinite. And of course, you're only going to find those in subduction zone terrains or ophiolites, because those are the only places that we're going to see commonly ultramafic rocks on Earth's surface. If you have a basalt that was metamorphosed to relatively low grade, you can use the term greenstone. And that's appropriate if you see minerals like chlorite, actinolite, epidote in the green schist facies in metabasalt. If it's not basaltic, you can use the term green schist. If you have a basaltic protolith and you've metamorphosed to the amphibolite facies, you can, and that you can identify plagioclase and hornblende in this rock, and you can see the black hornblendes there, and those are red garnets. You can call the rock an amphibolite. And in this case, because you have nice big garnet porphyroblasts, those large crystals, it's like a phenocryst for a metamorphic rock, but they're called porphyroblasts in a metamorphic rock. If you see those, you can use that to be even more specific about what kind of rock you're looking at. This is a garnet amphibolite, not just an amphibolite. In subduction zone terrains, you're going to see blue schists that don't always look quite as blue as this rock, but they do contain the sodium amphibole glaucophane that gives the rock its blue color. And in an eclogite, it's typically defined by the green amphicite, it's a clinopyroxene that occurs only at high pressures, and red garnets. So people often will call it the Christmas rock, but it will have more or less garnet depending on how the rock's feeling the day it was metamorphosed. Okay, you can have skarns that result from metamorphosed carbonate rocks, and skarns are typically fine-grained, and they also are a combination of calcareous silicate minerals, so calcium-bearing silicate minerals, as well as carbonates. So you see both in a skarn. In a granulite, remember that those are forming only at high temperature, so you've already driven off all the structural water in phyllosilicates and in hornblends. And in a granulite, you typically see only plagioclases and pyroxenes, both clinopyroxene and orthopyroxene. Or if the rock has gotten hot enough it started to sweat and you see pockets of melt, we give that kind of rock a name, metamorphic rock, a name of migmatite. So it's a mixture of melt as well as the remaining metamorphic rock. And you can be more specific about the terms. Generally, the darker parts of a migmatite are called the melanosome. You can think of melanin to give your skin a darker color, or a leucosome, which form the light pods of the partial melt that's not crystallized. Now, I've been using the term porphyroblast for a while, and porphyroblasts are these large crystals in any metamorphic rock that grew much larger than other minerals in that rock. And each individual crystal in this garnet and phyllite here, each individual porphyroblast is a porphyroblast, but the rock itself gets a textural term of porphyroblastic. In lower grade rocks, you still can get some porphyroblasts, but when they occur in slates or phyllites, you'll often hear the term spotted phyllite or spotted hornfells to indicate to whoever's listening to you or reading what you've written that there are porphyroblasts in there. And oftentimes they're small enough, they're hard to identify, and so we call them spots. Some other terms that you may run across: ortho, like ortho-gneiss, indicates that the protolith was igneous. It says no more or less than that, just that you had an igneous protolith. A paragneiss would be one that had a sedimentary protolith. And sometimes, you can't apply these necessarily in all cases. You don't know what the protolith was, whether it was igneous or sedimentary, but nevertheless, you'll see these terms. Now, the type of protolith is going to affect the chemistry of the rock and the minerals that grow during metamorphism. So, as I briefly mentioned before, iron and magnesium-rich mafic and ultramafic rocks, there are more nickel and chromium in the ultramafic rocks, more calcium in the mafic rocks. That's going to result in mafic minerals, calcium-bearing minerals in the resulting metamorphic rock. The trace elements, nickel and chrome, will be incorporated into either accessory phases that grow in small quantities in the metamorphic rock, or in the instance of chromium, that's going to have an effect on the pyroxene. So you may see chrome diopside with its very bright green color. If you're metamorphosing a shale, you have a lot of aluminum and potassium, silicon, you're going to end up with phyllosilicates, the muscovites, biotites, aluminosilicates because of the high aluminum content, quartz, and oftentimes feldspars, potassium feldspars in particular. If you're metamorphosing a carbonate, you have a lot of calcium, perhaps magnesium available, and you're going to grow carbonate minerals like calcite or like dolomite. And sandstones if they're relatively pure in silica, you're going to have a lot of quartz in the resulting metamorphic rock. A granite is a mixture of some of these. You're going to have quartz, K spars, sodium plagioclases, phyllosilicates, perhaps some aluminosilicates as a result. So when you're looking at mineral assemblages for each of these different kinds of metamorphic rocks, you have to keep in mind what were the ingredients that were put in from the protolith, those elemental ingredients that you're putting into your big stew pot and you're metamorphosing it, and what you get out of your stew is going to depend on what you put into your stew. Now, if there's some other terminology. If we're metamorphosing a clay-rich sediment, like a shale, we often discuss a pilitic protolith, and that simply is telling you that it was a clay-rich protolith like a shale. And the kinds of metamorphic rocks that you get out of a pilitic protolith are the foliated kind, because they have a lot of the phyllosilicates. We're going to see slates and phyllites, schists and gneisses. If you have a more sandy or a sandstone protolith, the resulting metamorphic rock is going to be referred to as having had a samitic protolith. And you're going to end up with a granitic gneiss or quartzo-feldspathic gneiss or quartzite. Basalts, you say they had a mafic protolith or a metabasite. And you're going to see terms like you saw on the metamorphic facies diagram, greenstone or green schist, amphibolite, or you'll have some kind of mafic gneiss or granulite, or perhaps eclogite or blue schist. Limestones and dolomites are said to be carbonate protoliths, and the resulting metamorphic rock is a marble. If you've got a mixture of shale and limestone, your protolith is a marl. And again, because of the shale, it's going to have a lot of aluminum, potassium, and you get these foliated metamorphic rocks, slate, phyllite, schist, and gneiss. I'll skip over the banded iron formation because that's not terribly common. Ultramafic rocks, when you have an ultramafic protolith, you get serpentinite. And then finally, with a granitic protolith, you're going to see granitic gneisses or granulites. Those also get called quartzo-feldspathic gneisses. So, depending on the grade, if you're looking, let's start with a pilitic protolith here. At lower grade, from low grade to high grade, you're going to see a change from clay minerals to chlorite to the micas, the aluminosilicates at intermediate grade, and then at higher grade you're going to get into garnets, staurolite, sillimanite, and perhaps orthopyroxene. Those are common minerals. If, however, you're looking at a mafic protolith, you'll start off with the prehnite and pompelliite because of their composition, plagioclases, epidote, chlorite, actinolite, those green schist facies minerals, hornblende and amphibolite facies, perhaps some garnet, biotite, and then the pyroxenes. With a carbonate protolith, of course, calcite and dolomite, plus or minus quartz. And then you're going to see these calcium-bearing minerals like the calcium amphibole tremolite or a calcium-rich garnet grossular. At higher grade, you'll see calcium-rich pyroxenes like diopside and wollastonite. If you're looking at ultramafic protolith in serpentinites, you're going to see talc, brucite, serpentine of the phyllosilicates. You may also see olivine and some of the pyroxenes, and the iron and magnesium pyroxenes in particular, perhaps some calcium pyroxenes like the diopside. In a granitic protolith, those minerals should look very familiar: quartz, K-spar, biotite, hornblende. And then at higher grades of metamorphism, you're going to see orthopyroxene and garnet forming from the iron and magnesium in the biotite and the hornblende. Now, this flow chart may be helpful to you. It requires that you understand some terms that we've been discussing in these modules. But if you follow it, you should be able to arrive at a decent metamorphic rock name. If we start up at the top with step 1, does the rock have a clear metamorphic microstructure or mesostructure? That means, can you see any kind of foliation or lineation? If not, maybe you need to say something about its protolith. Maybe you can call it a metabasalt or a metagabbro. That's one possibility. That's a very low-grade metamorphism. If you do see a metamorphic structure, and that could be an increase in the crystal size because of recrystallization, then you go to step 2, which is it appropriate to use a specific name for any of the following reasons? Does the rock have a composition? Is it composed of 75% or more of a single mineral? If so, maybe you just use the mineral name and add "ite" at the end, like amphibolite or garnetite. Is the mineral content or the structure of the rock, does it fit another specific name? Then you can choose one of the names that I'll show you on the next slide, that, like amphibolite, that would be appropriate. Or is the content of, or the origin of the rock known, and should it be emphasized? If not, then does the rock have a schistosity? If it doesn't, then you have a granofelsic structure or a texture, and you might see that it's got abundant kyanite in it. You would name it a kyanite granofels. Said and done. If it does have a schistosity, so a well-developed foliation, then you go to step 4 here. Is the schistosity well-developed, uniformly through the rock? And is it a narrow schistosity, less than 1 centimeter? What this is trying to get at is it schistose or is it gneiss? If it does have a very fine foliation, then it has a schistose structure, and it's a schist. And if so, then you might have a modifier like garnet mica schist. If not, then you come here. It has a gneiss structure. The rock is a gneiss. And then you might have some modifiers like that example below, biotite, feldspar, gneiss. So you might be able to follow this. It's still a little bit tricky because you have all these possibilities for involving the protolith name or choosing a specific metamorphic rock name that you're not quite familiar with yet. Here are some of those specific names that you can use. Amphibolite. I'll just work from top to bottom here. Amphibolite, dominantly amphibole, usually hornblende. Is it a blue schist? Does it have glaucophane in it? Is it bluish? It doesn't have to be schistose to be called a blue schist. In fact, the term blue schist is often applied to a mafic protolith. It might be a calc-silicate rock, and that's when you're going to see calcium and dolomite, perhaps, along with calcium-rich silicate minerals. Is it an eclogite? Does it have the garnet and amphicite, the red garnet and the green amphicite in it? Is it a green schist or a green stone? Well, you're looking for those green minerals, chlorite, epidote, actinolite, along with K-spar, and maybe quartz. Is it very fine-grained? Could it be a contact metamorphic rock? Or perhaps you have a marble that result from metamorphosing a limestone or a dolomite. Or a migmatite if melt is present. I will discuss myelinite in a later lecture when we do more on textures of metamorphic rocks. If it's a phyllite, if it has that slaty cleavage and it has a sheen from the growth of the muscovites or chlorites or biotites. Or perhaps it's a quartzite, if it's mostly quartz, or serpentinite if you have serpentine plus other magnesium or chrome-rich minerals, or a skarn if you have calcium and calcites, dolomites, or calcium silicates, and also fine-grained. Or perhaps it's a slate that has a very slaty cleavage, that's well defined, but there is no sheen to it because it hasn't been metamorphosed to a high enough grade to grow the phyllosilicates. So that's a rundown on the sorts of ways and names you can name a metamorphic rock. I don't expect you to be experts. This is going to take some practice. But try to apply what you've learned in lab, and I'll show you some examples in class before you get started. So what you learned in this module was about foliated metamorphic rocks, whether they're slates, phyllites, schists, or gneisses. I told you about coaxial and non-coaxial deformation. Think pancakes versus stretching. I told you about non-foliated metamorphic rocks, giving them a name of hornfels or granophyls. We talked about specific metamorphic rock names like marble, quartzite, and fibolite, and how the protoliths really control the chemistry of the resulting rock and the minerals that are within them. And then I gave you the IUGS flow chart that may help you to name metamorphic rocks as you learn how to do this.